Good evening. I'm Altaf Hussain, a former professor, Department of Chemistry, University of Dhaka, Bangladesh. I have some problem to continue the lecture series for last 2 or 3 weeks. However, I come back now. The last lecture was on A-level chemistry. Lecture was 24th lecture, and it was on chemical equilibrium. And this 25th lecture is a continuation of 24th lecture. So we talked about equilibrium, and we also talked about if we change the pressure, what happens on equilibrium and temperature, etc. So now I summarize that if we change pressure and if you have a reaction like this, nitrogen and hydrogen, which forms ammonia, equilibrium position shift towards product, that is form more ammonia if pressure increases. If we take another reaction, that nitrogen dioxide to nitrogen pentoxide, and if the equilibrium shifts then towards the reactant, more N2O forms. If we decrease pressure, then equilibrium position shifts towards the reactant, that is more nitrogen and hydrogen is formed. And similarly, if we decrease pressure for this reaction, the equilibrium position shift towards more nitrogen dioxide. Effect of temperature on the position of equilibrium. If we take a reaction like this, hydrogen iodide, which forms hydrogen gas and iodine gas, and it's an endothermic reaction. And then we see that if we increase the temperature, the equilibrium concentration of hydrogen iodide decreases. And the equilibrium concentration of hydrogen or iodine gas concentration increases. So next slide shows about endothermic reaction and exothermic reaction. We take an example of endothermic reaction here and an exothermic reaction over there. And then we see if we increase the temperature, position of equilibrium shift towards products, that is hydrogen, in this case, hydrogen gas and iodine formed. If it is an exothermic reaction, then position of equilibrium shift towards reactants. That means position of equilibrium shift towards sulfur dioxide and oxygen formed. The temperature decreases, position of equilibrium shifts towards reactant, more hydrogen iodide form, and position of equilibrium shift towards products, and more sulfur trioxide is formed. Well, then comes, what about, do catalysts have any effect on the position of equilibrium? Well, what is catalyst then? Catalyst which increases the rate of chemical reaction, or catalyst reduce the time taken to reach equilibrium. Therefore, we do not have any effect on position of equilibrium once we reached this equilibrium position with catalyst. So catalyst, in fact, catalyst has no effect on position of equilibrium. Next, what we talk about equilibrium constant. What is equilibrium constant? So here, the reaction hydrogen gas and iodine gas reacts together to form hydrogen iodide gas. And we have a temperature, fixed temperature, 500 degree Kelvin. And the equilibrium constant, we say like that, we define it like this: the product, concentration of product, N divided by concentration of the reactants. And if number of moles is there, so this is a square. We have 2 moles of hydrogen iodide, so concentration of hydrogen iodide is square. And then we take it data from here, you see, the concentration of hydrogen gas, concentration of iodine gas, and concentration of hydrogen iodide gas. If we have concentration of these of these three. And if we find out the equilibrium constant, we say that it's 161. And then comes out about a unit of it. We talk it in later slides, but then I show you that, you see, the equilibrium constant is almost equal, almost constant, and that's why you call it equilibrium constant for different concentration of the reactant and product of same reaction at a different at a constant temperature. Okay, then we go for this. We take a how do we express equilibrium constant? We take a general equation. That's m moles of A and n moles of B reacts together to form P moles of C and Q moles of D, where M, N, P, and Q are the number of moles, as I said, for the stoichiometric reaction, and it is a reversible reaction. And now we find out the equilibrium constant of this reaction. What is that then? Kc is the symbol of the equilibrium constant, which is equal to that concentration of product and its moles and concentration of reactant divided by concentration of reactant. You see that concentration of product and its moles, concentration of product D and its moles divided by concentration of A and its moles and concentration of B and its moles. So concentration of product is this and divided by concentration of reactant, and that is this subscripts are the number of moles of the product or reactant. So if we take this reaction, this is a general reaction, and we can express equilibrium constant for a general reaction like this. Once we know that, well, we could have different types of reaction, and a reaction we could have solid, we could have liquid, we could have gases, and etc. So when it is solid, a product is solid, we ignore solid concentration because solid concentration is same for. So the equilibrium constant for this reaction, that is silver ion aqueous solution and ferrous ion aqueous, and then silver solid and ferric ion. So equilibrium constant of this one, the product is silver solid and ferric ion. So since silver is a solid product, so we ignore this product and take the aqueous ion or ferric ion and then divide by reactants, that is silver ion and ferrous ion. And this is the equilibrium constant for this particular reaction where a product is a solid. Okay, then we go for unit of equilibrium constants. So how we can find out the unit of equilibrium constant? It depends on, you see, the reaction to reaction. We have here is a nitrogen and hydrogen forms ammonia gas, and we can have equilibrium constant for this case. Concentration of product, that is ammonia, and it has 2 moles, so we keep it to square, ammonia concentration of ammonia square, and then nitrogen, and then hydrogen, and concentration of hydrogen to the power 3. So if we know that concentration will be expressed in mole per dm cube, so here if we have mole per dm cube square, okay, and then here mole per dm cube, and then mole per dm cube cubes. So if we cancel it out, we find for this reaction, the unit of equilibrium constant is dms to the power 6 and per mole square. If we go for this one, you see, we can find it out and find this dm cube unit is dm cube per moles. So depends on the reaction of how it is. If we have same number of moles in reactant and product, then we do not have any unit. We do not have any unit to express. It cancels out each other. Okay, we take a working example. It's a ethanol reacts with ethanoic acid. to form what? To form ethyl ethanoate and water. We are saying that the 500 cubic centimeter of reaction mixture at equilibrium and the mole is 0.235 moles of ethanoic acid and 0.0350 moles of ethanol together, react together with and form 0.18 mole of ethyl ethanoate and 0.18 mole of water. We are supposed to calculate the equilibrium constant of this reaction. And so we know the concentration, we find out the concentration because we have the volume here and we have the mole, and then therefore we find out the concentration of ethyl alcohol and acetic acid, and then also the ethyl ethanoate and water. And this is the concentration of these product and reactant. So we can write down the equilibrium constant expression like this, and then we find out, you see here, the 1 mole of ethyl alcohol and 1 mole of ethanoic acid. Similarly, we have 1 mole of ethyl ethanoate and 1 mole of water. So in the product and also the reactant, the number of moles are same. Therefore, if we calculate out and find out that Kc, equilibrium constant Kc here is equal to 4.03, and it doesn't have any unit because the units here and here cancels out, and therefore we have only 4.03 is the equilibrium constant of these worked examples. Well, and if we want to have a note here, there are equal numbers of moles, as I said it on the top and bottom, then we see that equilibrium expression, we do not have any unit in it. Okay. Second worked examples, it was said that 1 mole of NaCl gas was enclosed at a 0.5 dmq flux at 298 degree Kelvin. The amount of NO gas, nitrogen oxide gas, in the flask at equilibrium was found to be 0.33 mole. Calculate the value of Kc of this reaction. That's what is the problem for us. So what we have to do now, we have to find out write down the equation of this reaction. We have to give a reversible equation of this one, and then we can write underneath write first the initial amounts, and then the third point is then write the given amount at equilibrium, and then the next part is calculate the equilibrium amount not given here, taking into account the number of moles of each substance showing in the equation for the reaction. And the next one, we start calculating the equilibrium concentration given in the volume of the solution, and finally substitute the values of unit of expression of equilibrium constant. And if we do so, we can calculate out in these 5 steps and then find out the equilibrium constant of this reaction, and that is Kc is equal to 0.080 mole per dmq. Okay, we were talking about concentration, but we do have gas reactions, many gaseous reaction, and then there is another possibility of finding out equilibrium constant by partial pressure. So that one is designated or symbolized as Kp, not Kc. Kc means equilibrium constant in terms of concentration, and Kp means equilibrium constant in terms of pressure. Okay, you see, we have 3 boxes here. We have gas A here, and then gas B is there. So partial pressure of gas A, let's say this is 8 and 8 Pascal, and this is 3 Pascal for gas B. The total pressure then gas A plus gas B is equal to total pressure, so we get 11 Pascal. It's a very simple thing. So what we are doing here, total pressure of a gas equals the sum of partial pressures of individual gases. So we have to see what is our reactant, what is our product, and then finally find out the Kp, and which is almost equal like to Kc. So we go for the next slides. We take an example of, again, you might ask why I'm taking again the same example. You will see that this nitrogen and hydrogen giving us ammonia, and it's a very important reaction, industrial reaction, Haber process. And we have to optimize this reaction using equilibrium, concentration, and etc. Therefore, I'm taking this example again and again. You see, for using this partial pressure, what we symbolized it, partial pressure with P, and then reactants and products are written as subscript after the pre. As you see, reactant, this product, the P subscript is ammonia, and then a reactant P subscript is nitrogen and subscript is hydrogen. And then we write down the moles in a superscript. So you see for ammonia, it's 2 moles superscript here, and for hydrogen and nitrogen do not is 1 mole, so we don't need to write P1 here, and then the hydrogen, the 3 moles, so we have right here 3 moles like this. So what are the units of Kp then? As usual, we express pressure in pascals, is it not? So Pascal is the unit, and the units of Kp depends exactly like Casey. It depends on the form of equilibrium expression. On the form of equilibrium expression, you see here we have equilibrium expression. So here Pascal into Pascal, here Pascal, and then 3 pascals, Pascal, Pascal, Pascal. So therefore, it depends on the expression here, and then we'll find out the unit of this. And then another thing, we do express pressure in Pascal, but in many chemist and chemical industries, we use atmosphere. 1 atmosphere is equal to 1.01 into 10 to the power 5 Pascal. Okay, we go to the next one, and then we take a workout example. You see sulfur dioxide reacts with oxygen, we get sulfur trioxide. Okay, it was said that the partial pressure of each gas of the following reaction is given below. Calculate the value of the Kp of this reaction. Partial pressure for sulfur dioxide is 1 into 10 to the power 6 Pascal. For oxygen is 7 into 10 to the power 6 Pascal. For sulfur trioxide, it's 8.0 into 10 to the power 6 Pascal. So if we write down the Kp, that means partial pressure, equilibrium constant in terms of partial pressure, and then we find out this with this value, and it is 9.1 into 10 to the power minus 6 in per Pascal. The units, how correct units we get here, Pascal into Pascal, and here, as I said, 1 Pascal, and then Pascal, 3 times Pascal. So Pascal. So therefore, these 2 cancels out, this 2 cancels out, and I got 1 by Pascal, that means per Pascal. So equilibrium constant in terms of pressure with 9.1 into 10 to the power minus 6 per Pascal. Okay. Well, I said there are very interesting application of equilibrium constant in chemical industries, and mentioned about ammonia, Haber process to produce ammonia, and this is an exothermic reaction, and how an exothermic reaction is with temperature and with pressure and with how it depends on that, what we have discussed in last slides, and I just summarized it here. And then what happened when we produce sulfuric acid, it's also an exothermic reaction. So we can find out all these together, and that is what is chemical equilibrium, and which is very important for our applications in industries, chemical industries. So this much we can have AS level chemical equilibrium, and in next class, next lecture, I'll go for organic chemistry. because we have finished the physical and inorganic part of syllabus of AS level, and we start on some lectures of organic chemistry in next lectures, few lectures. Maybe we take about 8 to 10 lectures for organic chemistry to cover up the syllabus of organic chemistry of AS level. Thank you very much for your patience. I hope this you will find this useful in handling chemistry, AS level chemistry. Thank you all.